Let a(n) be the sequence defined by a of 1 equals 2 and a of n plus 1 equals a to the n to the power of n plus 1 minus 1 for each integer n greater than or equal to 1. Suppose that p is greater than 2 is prime and k is a positive integer. Prove that some term of the sequence an is divisible by p to the power of k. So let's try out simpler cases. First, let's try looking at k equals 1. How do we solve k equals 1? Well, we have this exponent m plus 1 here, and we want this to be divisible by p. And this means that a to the n to the power of n plus 1 is equivalent to 1 mod p. This really reminds us of Fermat's little theorem, so we can try applying that. Specifically, if we want to make this exponent p minus 1, we can try making n equal to p minus 2. Doing that, we end up getting a of p minus 1 is equivalent to a of p minus 2 to the power of p minus 1 minus 1. Now there are two cases from here. If a of p minus 2 is divisible by p, then we just use that p minus 2 to get that k equals 1 works. Otherwise, we can use Fermat's little theorem to show that this thing here is congruent to 1 modulo p, and therefore this is 1 minus 1, which is 0 mod p. Now let's try solving the problem for general k. Given this p to the k here, we are motivated to build upwards, starting from p to the k, then we can use that value of n to bring up to p to the k plus 1, and so on and so forth. So let's try this out. Suppose we start with a of n is equivalent to 0 mod, and to keep things simple, I'm just going to go ahead and say mod of p. Then this means that a of n is equal to kp for some positive integer k. Then plugging this into a of n plus 1, we end up getting k to the p to the n plus 1 minus 1. And then plugging this into a of n plus 2, this is equal to k to the p to the n plus 1 minus 1 to the n plus 2 minus 1. Now we see something special happens when n is even. If n is even, then the coefficient of 1 that is not divisible by p here is just negative 1 to the n plus 2, which is 1. And the 1's cancel out here, and this expression is divisible by p to the n plus 1, which is surprising. Therefore, we can try splitting into cases on whether an even n exists or if no such even n exists. Let's go ahead and call a prime p good if there exists an even n such that a of n is equivalent to 0 mod p, and then bad otherwise. Now let's go ahead and solve the problem for good n. Given this idea above, we can go ahead and do this. So let's go ahead and let n equals 2k such that a of 2k is equivalent to 0 mod p. Then a of 2k is equivalent to some positive integer x times p. Then plugging this in as above, we get a of 2k plus 2 is equal to xp to the 2k plus 1 minus 1 to the 2k plus 2 minus 1. Then if we take this mod p to the 2k plus 1, inspired by the fact that we have the minus 1 stray here, then this is equivalent to minus 1 to the 2k plus 2 minus 1, which is equivalent to 1 minus 1, which is equivalent to 0 mod p to the 2k plus 1. And in particular, a to the 2k plus 2 is equivalent to 0 mod p. This inspires us to use induction to build up. In particular, we conjecture the following, that p to the 2k plus 2m minus 1 divides a of 2k plus 2m for all positive integers m. So now let's prove this. For m equals 1, we've just proven this above, right here. Now assume that the step holds for m. That is, we have that this is true. Then a of 2k plus 2m is equivalent to 0 mod p, obviously. Then applying the claim here, what we've just shown here, we end up getting, by increasing this by 2, we get that this is equivalent to 0 mod p to the power of this thing plus 1, which is 2k plus 2m plus 1. And since 2m plus 1 is 2 times m plus 1 minus 1, and 2m plus 2 is 2 times m plus 1, we've proven our claim using the induction. And in particular, if we take m to be large enough, then we have that a to the 2k plus 2m plus 2 is equivalent to 0 mod p to the power of this thing. So if we keep increasing m, we end up proving the problem for all good primes p. Now that we've solved the problem for good primes p, now we turn our attention to the bad primes p. And in which case, there's no even integer such that a of 2 to the k is equivalent to 0 mod p. No such k exists. And we want to solve the problem in that case. So now what? Well, inspired by using the p minus 2 as shown above, and the p minus 1 especially working well with Fermat's little theorem, we can try generalizing. So suppose that we have an integer z is equal to x times p minus 1. Then we could try using a of z is equal to a of z minus 1 to the power of z minus 1. Now there are two cases from here. If a of z minus 1 is 0 mod p, then we are fine. If it's not 0 mod p, then Fermat's little theorem implies that since z is just x to the p minus 1, we have a p minus 1 here, so that becomes 1. So this is 1 to the x minus 1, which is equivalent to 0. Therefore, p divides a of z. However, since p is an odd prime, p minus 1 is even, and so z is even. But this means that the prime p is good by definition, which is a contradiction because we are dealing with p that are bad. Therefore, we must have that a of z minus 1 is equivalent to 0 mod p. Now, what's the next thing we do after this? Well, you guessed it, we just plug into a of z minus 1. Doing so, we end up getting a of z minus 2 to the z minus 1 minus 1 is equivalent to 0 mod p. Then moving the 1 to the other side, we end up getting that this is equivalent to 1 modulo p. And now we deal with cases again. If a of z minus 2 is equivalent to 0 modulo p, then this entire thing becomes 0, and we do not want that. Therefore, assume that a of z minus 2 is not divisible by p, so we can yet again apply Fermat's little theorem. If we move this 1 to the denominator, then this numerator here, by Fermat's little theorem, since it's x to the p minus 1, is just equivalent to 1. So therefore, this is equivalent to 1 to the x over a to the z minus 2, which is equivalent to 1 over a to the z minus 2, a of z minus 2, which is equivalent to 1. And therefore, we have that a of z minus 2 is equivalent to 1 mod p. At this point, we're kind of stuck because we can't continue doing this forever. At this point, we now look back at our formula here, and seeing that a of z minus 2 inside here is equivalent to 1 inside here, we can say this is z minus 1. We can now apply the lifting exponent lemma, which states that if Vp denotes the highest power of p dividing a certain integer, I'll go ahead and denote it Vp of n, then we have the following. VP of a to the n minus b to the n is equal to VP of a plus b, plus v minus b, plus VP of n. If a is equivalent to b modulo p, which is not equivalent to 1, and p is a non-prime. If we plug in a equals a of z minus 2, and b equals 1, and n equals z minus 1, we end up getting that this is equal to VP of a of z1 minus 1 by definition is equal to VP of a of z minus 2 minus 1 plus VP of z minus 1. We have lots of freedom over z minus 1 as control to the a of z minus 2 and a z minus 1, so we can try controlling that. Ideally, we want k to be a positive integer such that this is greater than or equal to k, because then that would make this greater than or equal to k because this is an integer. And this makes us want to set z is equivalent to 1 modulo p to the k. At the same time, we have that z is equivalent to 0 mod p minus 1, so we have lots of restriction here. Is this a big deal? No. By the Chinese Remainder Theorem, these two conditions can both be satisfied. Therefore, we can choose a z such that this is satisfied, and so is this one here. And then we then have that this is greater than or equal to k, and so p to the k divides a of z minus 1. And taking k to be arbitrarily large, we solve the problem for bad primes p as well. Therefore, we've exhausted all cases and have solved the problem for all primes p and all positive integers k. So thank you so much for watching this video. Please subscribe if you'd like to see more.